A t-test is a statistical tool that helps you decide whether a difference you see in numbers is real or just due to random chance. There are three most common flavors. One sample t-test. Imagine you run a pilot program in a single store and you want to know if the average sales increase, say $5,000, is different from the company-wide historical average, $4,800. You compare one sample mean to a known benchmark. Independent samples, two-sample t-test. You have two separate groups that do not influence each other, such as sales teams in two different regions, and you want to know if their average monthly sales differ. Each observation belongs to exactly one group. Paired samples, dependent t-test. You measure the same unit before and after an intervention, like the profit of a store before and after a new promotion. Because the two numbers come from the same store, they are linked, paired. The test looks at the average of the differences. Choosing the right version is like picking the correct wrench size. Use one sample when you have a single set and a known target, independent samples for two unrelated groups, and paired samples when the data points are naturally connected. Every statistical test starts with two competing statements. Null hypothesis, H0, the default claim that there is no effect or difference. It is what you try to disprove. Alternative hypothesis, H1 or HA, the claim that there is an effect or difference, the one you hope to support. For each t-test, the format is similar, but refers to the appropriate means. One sample. Null hypothesis mu equals mu0, the population mean equals the benchmark mu0. Alternative hypothesis mu not equal to mu0, two-tailed, or mu greater than mu0 or mu less than mu0, one-tailed. Independent samples. Null hypothesis mu1 equals mu2, both group means are equal. Alternative hypothesis mu1 not equal to mu2, two-tailed, or mu1 greater than mu2 or mu1 less than mu2. Paired samples. Null hypothesis mu d equals 0, the mean of the difference scores d equals x post minus x pre is 0. Alternative hypothesis mu d not equal to 0 or greater than 0 or less than 0. Writing them in plain language helps MBA students. There is no difference in average profit between region A and region B, null hypothesis, versus region A's profit is higher than region B's, alternative hypothesis. A t-test works only if the data behave in a certain way. Think of the assumptions as the road conditions required for a smooth drive. Normality, the distribution of the variable or the differences for paired tests, should look roughly bell-shaped. Small samples less than 30 need this more strongly. Larger samples rely on the central limit theorem. Independence, each observation must not be influenced by another. In a store-level study, sales of store 1 should not affect sales of store 2. Equal variances, homoscedasticity. For the classic independent samples t-test, the spread variance in group 1 should be about the same as in group 2. You can check this with Levine's or Bartlett's test. If variances differ noticeably, use the Welch adjustment, which modifies the formula for degrees of freedom and does not pool the variances. It is like switching to a car that can handle a bumpy road. The test stays valid. Explanation. The core of a t-test is the t-statistic, which tells you how many standard errors the observed difference is away from the null value. For a one-sample test, t equals x bar minus mu0 divided by s over square root n, where x bar is the sample mean, mu0 the benchmark, s the sample standard deviation, and n the sample size. For an independent samples test with equal variances pooled, sp squared equals open fraction left parenthesis n1 minus 1 right parenthesis, s1 squared plus left parenthesis, n2 minus 1 right parenthesis, s2 squared over n1 plus n2 minus 2. T equals x bar 1 minus x bar 2 divided by sp square root of 1 over n1 plus 1 over n2. Degrees of freedom df equals n1 plus n2 minus 2. When variances are unequal Welch, use separate variances. T equals x bar 1 minus x bar 2 divided by square root of s1 squared over n1 plus s2 squared over n2. df equals open fraction left parenthesis s1 squared over n1 plus s2 squared over n2 right parenthesis squared divided by left parenthesis open fraction s1 squared over n1 squared over n1 minus 1 plus s2 squared over n2 squared over n2 minus 1 close fraction. Welch-Satterthwaite. For a paired samples test, T equals d bar divided by SD over square root n, where d bar and SD are the mean and standard deviation of the different scores, and df equals n minus 1. These formulas turn raw numbers into a single t value that can be compared to a reference distribution. Explanation: once you have the t statistic, you need to know how likely it is to appear if the null hypothesis were true. This probability is the p-value. Locate the absolute value of t on a t distribution table, or use software with the appropriate degrees of freedom. For a two-tailed test, multiply the one-tailed tail area by 2. For a one-tailed test, use the single tail area. Compare the p-value to the chosen significance level alpha. Common alphas are 0.05, 0.01, and 0.1. If p is less than or equal to alpha, reject H0. Result is statistically significant. If p is greater than alpha, fail to reject H0, insufficient evidence. Critical values are the t-scores that correspond exactly to alpha. For example, with degrees of freedom equal 20 and alpha equals 0.05, two-tailed, the critical value is about plus or minus 2.086. If your calculated t is beyond plus or minus 2.086, you reject H0. In business language, statistically significant at the 5% level means there is less than a 5% chance that the observed difference is just random noise. A confidence interval, CI, gives a range of plausible values for the true mean or mean difference, and is directly linked to hypothesis testing. For a one-sample or paired samples confidence interval, x bar plus or minus t sub alpha over 2, df, times s divided by the square root of n. For an independent samples confidence interval with equal variances, x bar sub 1 minus x bar sub 2 plus or minus t sub alpha over 2, df, times s sub p times the square root of open fraction 1 over n sub 1 plus 1 over n sub 2 close. If the confidence interval does not contain the null value, 0 for differences, mu naught for one sample, the test will be significant at the same alpha level. Conversely, if the null value lies inside the interval, you would not reject H0. In practice, an MBA student can report, the 95% confidence interval for the profit lift after the promotion is $1,200 to $3,400. So we are 95% confident the true lift is positive, confirming the promotion's effectiveness. A one-sample t-test. A retailer claims the new loyalty program raises average monthly spend to $120. A random sample of 16 customers shows X bar equals $115, S equals $20. Test at alpha equals 0.05. 1. Null hypothesis mu equals 120. Alternative hypothesis mu not equal to 120. 2. T equals 15 minus 120 divided by 20 over root 16 equals negative 5 divided by 5 equals negative 1.0. 3. Degrees of freedom equals 15. Critical t for two-tailed test at 5% approximately plus or minus 2.131. 4. Absolute t equals 1.0 less than 2.131, so we fail to reject the null hypothesis. Not significant. 5. 95% confidence interval. 115 plus or minus 2.131 times 20 over 4 equals 115 plus or minus 10.66, giving $104.34 to $125.66. The hypothesized $120 lies inside, agreeing with the test. B. Independent samples t-test with equal variances. Two stores launch different price promotion tactics. Store A, sample size 12, average sales $8,500, S equals $900. Store B, sample size 15, average sales $7,800, S equals $850. Test if means differ, alpha equals 0.01. 1. Null hypothesis mu A equals mu B. Alternative hypothesis mu A not equal to mu B. 2. Pooled variance S sub P squared equals 11 times 900 squared plus 14 times 850 squared divided by 12 plus 15 minus 2, approximately 761,000. So S sub P is approximately 872. 3. T equals 8,500 minus 7,800 divided by 872 times root 1 over 12 plus 1 over 15. approximately 2.07. 4. Degrees of freedom equals 25. Critical T for two-tailed test at 1% approximately plus or minus 2.787. 5. Absolute T equals 2.07 less than 2.787, so we fail to reject the null hypothesis at 1%, though it would be significant at 5%. See paired samples t-test. A coffee chain measures daily revenue before, pre, and after post, a new music playlist for 10 days. Differences post minus pre in dollars: 120, 85, 95, 110, 70, 130, 190, 115, 80. 1 D bar equals 99.5. 2 S sub D approximately 18.2. 3 T equals 99.5 divided by 18.2 over root 10, approximately 17.27. 4 degrees of freedom equals 9. Critical T for two-tailed test at 5% approximately 2.262. 5 absolute T much greater than 2.262, so we reject the null hypothesis. The playlist significantly raises revenue. These step-by-step examples illustrate the mechanics that exam questions expect. When you decide to reject or not reject a hypothesis, two kinds of mistakes are possible. Type I error: rejecting a true H0, a false alarm. Its probability is the significance level alpha, e.g. 5%. In business, this would be like concluding a new marketing tactic works when it really does not, possibly wasting money. Type II error: failing to reject a false H0, missing a real effect. Its probability is denoted beta. Power equals 1 minus beta, the chance of correctly detecting a true effect. Power depends on 4 factors. Effect size: larger true differences are easier to detect. Sample size and more observations reduce the standard error, increasing power. Variability: sigma lower variance improves power. Alpha level: a larger alpha, e.g. 0.1, makes it easier to reject H0, raising power, but also raising type I risk. Sample size calculators for t-tests work backwards given desired power, often 80% or 90%, expected effect size Cohen's d alpha and variance, they output the needed n. For an MBA, remember the rule of thumb: to detect a medium effect D approximately 0.5, with 80% power at alpha 0.05, you need about 64 observations per group for independent samples. From this explanation, you just need to break them into segments, and for each segment return phonetic reading style of the segment. Effect size quantifies how big the difference is independent of sample size. The most common metric for t-tests is Cohen's d. For independent samples with equal variances, d equals x bar 1 minus x bar 2 divided by s sub p. For a one-sample or paired test, replace s sub p with the sample standard deviation, or SD, of differences. Interpretation Guidelines, Cohen 1988. D approximately 0.2, small effect. D approximately 0.5, medium effect. D approximately 0.8, large effect. In exam answers, after reporting the p-value, you should also comment on practical relevance. Although the difference is statistically significant, p equals 0.03, the effect size d equals 0.25 indicates only a small practical impact, suggesting the new pricing rule may not justify implementation costs. Typical MBA exam prompts are built around business scenarios. Data selection question: a company tests 2 sales training programs on separate groups of 30 salespeople each. The mean quarterly sales are 45,000, standard deviation 8,000 for program A and 42,500, standard deviation 9,500 for program B. Which t-test should you use and why? Use an independent samples t-test because the 2 groups are distinct and observations are independent. Check variance equality. If Levine's test is significant, apply Welch's adjustment. Computation question: using the data above, test at alpha equals 0.05 whether the programs differ in mean sales. Show all steps, compute t, degrees of freedom, p-value, and state the conclusion. Provide pooled variance, calculate t approximately 1.09, degrees of freedom 58, critical t approximately 2.001, p greater than 0.05, fail to reject H0. Include 95% confidence interval for the difference and compute Cohen's d approximately 0.27, small effect. Interpretation question. A manager claims a new inventory system reduced stock outs from an average of 12 per month to 8 per month. A sample of 20 months after implementation shows a mean of 7.5, standard deviation 3. Test the claim at the 1% level and discuss both statistical and practical significance. Use a one-sample t-test, null hypothesis mu equals 12, alternative hypothesis mu less than 12. Compute t approximately negative 7.07, degrees of freedom 19, p less than 0.001, reject h0. The reduction is statistically significant. Cohen's d equals 12 minus 7.5 divided by 3 equals 1.5, large effect,